So got so caught up in the technical problems. Sorry, folks, those of you just watching the recording, missed the first minute here. Anyhow, now when we combine the like terms, we get the 2x that we want. Okay. Again, we'll pretend we don't notice anything useful yet, and we'll do this string of examples down here. If we multiply this, we get x squared plus 2x plus 7x plus 14. And collecting the like terms, we get x squared plus 9x plus 14. And in the fine print here, like a letter from the bank, we asked the question, what's special about 2, 7, 9, and 14? Well, 2 and 7 were the numbers in the parentheses. When you add 2 and 7, you get the coefficient for the middle term, you get the 9. And when you multiply 2 and 7, you get the constant term at the end, you get the 14. This is like a dependable connection here. Let's do another one, and then we'll make a statement down here. If I multiply this out, we get x squared plus 9x minus 3x minus 27, which collapses to x squared plus 6x minus 27. So what's special about negative 3 and 9? Negative 3 and 9 are the numbers used in the factors. Negative 3 added to 9, add them, and you get the middle coefficient. Multiply them, and you get the constant term. So again, going back here, if we add the 2 and 7, we get 9. Multiply them, we get the 14. If we add negative 3 and 9, we get 6, and we multiply them, we get negative 27. Hey, how is this one different? You see the difference in the startup. We got this little 3 here. Okay, so if we multiply this out, 3x times x is 3x squared, and then 3x times 5 is 15x. 8 times x is 8x. 8 times 5 is 40. Combine the like terms, we get 3x squared plus 23x plus 40. So if you add 8 and 5, you don't get 23, don't you? If you multiply them, you still get the constant term. But now we can't say, oh, add those numbers and you get the middle coefficient. And the reason it doesn't work here is because of, we all love the number 3. It's a useful number, but the 3 is what's causing the problem. The 3 makes it so that that idea of adding these numbers to get the middle coefficient doesn't work. So if we need to factor something where it's just a 1x squared, when there is no 2, 3, 7, or whatever in front of the x squared, all we need to do is to find two numbers that add up to b, add up to the middle coefficient, and multiply out to the constant term at the end. So what we're going to write here is finding two numbers that have a product, oops, not with the highlighter, silly person, product equal to c, which is the math talk way of saying find two numbers that when you multiply them, make the constant, have product c and sum equal to b. We want those same two numbers to add up to the coefficient in the middle. And now we will practice using that. Okay. When somebody put some advice in the checkbox, I mean in the text box. And Lauren, if you go to the modules, go to Carmen and go to modules in week 1, in week 1, you'll see something that looks like this. Something labeled with a 2. That's today's lesson. Okay. Sorry if you're having the rest of you. Did you get the notes? Okay. Yeah. Yeah. It takes a week to learn where everything is and all that, including for myself. After 3 days of struggling, I finally managed to get into the electronic textbook for my Math 1050 class. They got an electric book now, an e-book now. As a strategy for factoring these things, what we can do, either mentally or on paper, is start by making an exhaustive list of all the ways you could multiply and get that constant term. So for 10, we could do 1 times 10 or 2 times 5, and that's it. There's no other way you can multiply some whole numbers and get a 10. Next, we investigate the factors we found and say, do any of them add up to the number in the middle? Do any of them add up to 7? Well, there you go. So we're done. I'm going to write, instead of writing up there where it's crowded, I just write x plus 2, x plus 5. If we would multiply that out, it would bring back x squared plus 7x plus 10. This is the factoring for x squared plus 7x plus 10. Let's try that same strategy here. What can you multiply to get 35? There's not a lot of choices. 1 and 35, 5 and 7, and that's it. That's a complete list of all the ways you could multiply and get 35. Do we need a 36 in the middle? No. Do we need a 12 in the middle? Yes, we need 12 in the middle. 5 added to 7 makes 12. So we're done with this. X plus 7, x plus 5. And in case anybody's wondering, you could put the 5 and then the 7, or the 7 and then the 5. Since it's multiplication, it does not matter. Are we all? Yes.
For our exams,
Yeah.
Is this okay, or should we show the work to get to
That's a good question. Probably, for something with numbers this mentally manageable, I don't think anybody's going to think you cheated or anything if you don't make this list. This one, maybe I'll try to get a better answer for you next time. It's common sense. Do you read? Some of you can do this right now. Find 2 numbers that multiply out to 30 and add up to 11. But a lot of us have to write the list down. I'm going to write 1 and 30. And it is good to exercise writing this list a little bit, because that's going to come in handy when we get to this next idea of declaring something a prime polynomial. So if I do 1 and 30, 2 and 15, I want to be very careful not to skip any possibility. 3 and 10, 5 and 6, and now I'm done, because the next would be 6 and 5. So it just starts repeating in reverse order. So there's 4 different ways we can multiply whole numbers and get 30. Do any of them add up to 11? There you go. Those have a sum of 11. So this will factor x plus 5, x plus 6. Look okay? Okay, and somebody, the Zoom link for this class meeting is always on Carmen. The links for the whole semester are on Carmen right now. All you have to do is go to the home page and look on the left-hand column and find the word Zoom and click there, and you'll see meetings going all the way into the first week of December. If you don't, stick around after we're done with the lesson, and I'll do a tour with you. We already made the list for 30. Do any of the pairs add up to 13? Yeah, right here. So we'll use 3 and 10 for this one. X plus 3, x plus 10. Okay. Let's try this one. exhaustive list of the ways to multiply and get 7 is that's it. That's the only way you can multiply and get 7 with whole numbers. And 1 plus 7 is 8. We've got a 6 in the middle. That means this is impossible to factor. And so we say that it is a prime polynomial. Cannot be factored. And in real life, prime polynomials are terribly useful things. They're used in encryption. Everybody familiar with that word these days? Encryption, like in banking machines and websites and everything else. And all sorts of, if you've got nothing to do later today, you Google uses of prime polynomials. Oh my gosh, golly, you'd be surprised all that's there. So how do we know a quadratic polynomial is prime? Is this: if none of the factorings of C have a sum equal to B. Well, if you make a complete list of all the ways you can multiply and get that number at the end, and none of them add up to the number in the middle, and that's for when it's a 1x squared, then you can say, well, there's no way to do this.
What is it called when we subtract it to get 6? So if we would have just did set, x plus 7, x minus 1.
Yeah, well, that would come up. Oh, you're not going to be able to subtract here because everything's plus signs.
Oh, okay, gotcha.
Feel free to experiment. If you put like x minus 1 and x plus 7, those will add up to 6. But now when you multiply, you're going to get -7, not +7.
Gotcha.
Yeah. Keep thinking. That's good thinking there. Here's the how many ways can we factor and get 24? This is where you might start saying bad words under your breath. 1 and 24, 2 and 12, 3 and 8, 4 and 6, and that's it, right? Next would be 6 and 4. It starts repeating itself. So can we factor this? Let's see. Let me change ink color for a moment. 1 and 24 add up to 25, 2 and 12 add up to 14, 3 and 8 add up to 11, 4 and 6 add up to 10. So there's the 14. We can factor this. We can factor this with x plus 2, excuse me, x plus 12. And since we've made this list, can we get an 11 in the middle? Yeah, I just said that a moment ago. We can use 3 and 8. 3 plus 8 add up to 11. 3 times 8 multiply out to 24. This will factor x plus 3, x plus 8. And there's the one using the 25. There's a 25 in the middle. And we can factor this x plus 1, x plus 24. Those multiply out to make the 24, and they add up to make the 25. Okie doke. Oh, I forgot that I'm not in the actual classroom now. I got to get this. I got a little document camera here. One moment, please. Show you something. If you've got a graphing calculator, you're going to love this. If you don't have a graphing calculator, you can use the online graphing calculator, Desmos or something else. But if you're going to take more math classes, and if you want to get the most out of this class, you might want to invest in one. So let's see now. see that screen? Is that visible? If I hit one,
Yeah, I can see it.
okay,
I
thank you.
can.
Thank you. All right, so here's a trick. You push your equation editor button, which is this y equals button, and you make an equation simply whatever the number is that you're trying to multiply and get. In this case, is 24. Make the first equation 24 divided by x. And if you haven't used the calculator much, the x key is right here. So I type in 24 divided by x. Okay. Now, if I hit the shift key, the second key, and the window key, which brings up, see the blue ink table set, which has nothing to do with dinner. It's how the table, the chart will be set up. Table start, that's just gonna be where you put it. Where do you want to start with your x values? I'm going to start at 0. This little triangle table, that's red delta table, really. That's where you tell the calculator if you want to go like 0, 1, 2, 3, or if you want to go 5, 10, 15, 20, or you want to put decimal in there, you can put whatever you want. And this is a long story, but have them both set to auto. Okay. Now, if we hit the second key, the second key and graph, we get the table. And what's displayed here are pairs of numbers that multiply out to 24. 1 times 24, 2. So it's the same thing we did a few minutes ago. And of course, some of them, if we keep going, it'll give you some 7 times, and this is rounded off, but you know, you can multiply 7 times something and get 24, but it won't be a whole number. So there's all the possibilities. And even going into using, if I scroll up, see, like -4, -6, those multiply out to 24. Okay, but wait, there's more. We'll make a second equation using 24 divided by x again, which will be the number from that live transcription. Okay, we can do that. And then plus x. So it's going to take that number from the first chart and add it to the x input. And if we look at the table now, see, now what's happening is you're getting the pairs of numbers that multiply out to the number in question here, the 24, and the third column is adding them for us. How cool is that, right? So if we look at the next exercise on you're still seeing my screen share, right? My worksheet. We want a 12 in the middle. If we look in this column for 12, look closely over there for 12, goes from 25, 14, 11. There is no 12. There's no way. And we knew this from pencil and paper a few minutes ago. All the possibilities are right here. You can't factor this. We can get right on here and say, well, this can't be done, so this is prime. Also, whether you're looking at the calculator or the pencil and paper, you can't get a 16, so that's also prime. And what about 10? You can get 10, 4 and 6. You don't want to get lulled into complete. You know how you do like 3 things in a row and they're sort of similar, and then your brain tends to assume the next thing is going to be the same trick, but that's not always the case. All right, looking at sign behavior in agonizing detail, when we don't even have to fill all this stuff in. This is just to make sure you get the the gist of things here. It's pretty easy. If everything's plus signs, you'll have plus signs in both sets of parentheses. So you know what, I'm gonna go back and we'll fill this in. This would be x plus 6, x plus 5, right? If you have a positive constant at the end and a negative in the middle, you're multiplying two numbers and you want them to multiply out to positive. So either they have to both be negative or both be positive. And you just end that. Open up some bandwidth. They must both be negative to add up to a negative 11 in the middle. So this would be x minus 6, x minus 5. Where it gets a little more interesting is here when you have a negative constant term. Remember, if you're going to multiply two numbers and get a negative answer, then one of them must be negative and the other positive. And it matters very much which we use here. We're going to use the 6 and the 5 again, but now we're going to add a negative and a positive, meaning we'll actually subtract, right? And if we do 6 and negative 5, we'll get 1. If we do negative 6 and positive 5, we'll get negative 1. The unwritten middle coefficient here is positive 1. So that means we want to let 6 be the positive number and 5 be the negative number.
I have a question.
Sure.
Why are we using 6 and 5 if there's no 11 in front of the x?
Because we're not really using 6 and 5. We're using 6 and negative 5. And 6
okay.
and negative 5 add up to 1.
Okay, yeah, that makes sense.
Okay, sure.
Mhm.
And then the next one, the middle coefficient is negative 1. So we're going to use the negative 6 and the plus 5. See, those multiply out to negative 30 and they add up to negative 1. That's why they work. That's why we choose them. Now we've got some trinomials here that were sloppily written. They're not in order. So here's some advice. Make sure you factor out any GCF and put the polynomial. What in the world does this mean? Descending degree order. It means just put things in order according to the exponents with the highest exponent first. So we put the square term first, and then the linear or first power term, and then the constant term. And then it's easier to work with. This would be x plus 2, x plus 7. Right? Those multiply out to 14 and add up to 9. What about this one? We'll rewrite it. X squared plus 11x minus 26. Much better. How can you multiply and get negative 26? How about a negative 2 and a 13? And those add up to positive 11, don't you? X minus 2, x plus 13. And then the last one in this little group, x squared plus 9x plus 20. Can you multiply and get 20 and add and get 9 with the same two numbers? How about a 4 and a 5? X plus 4, x plus 5. That does the trick, right? Here's some that have a GCF. GCF here would be 5. 5 times x squared plus 6x plus 8. Excuse me. And then we're not done. We've got the GCF out there. We want to pay careful attention to not losing it, not misplacing it, because it's part of our answer. And do we have two numbers that add up to 6 and multiply out to 8? What do you think of those? 2 and 4. X plus 2, x plus 4. I got dust on my iPad. We doing okay? All right. See a little more interesting GCF here. We can yank out a 3 and the variable p and x to the second power. I'm going to write 3p x to the second power. And then we need an x squared. See, that'll make 3px to the fourth, and then minus 5x, that'll make minus 15px cubed. And then minus 14 would bring back this last term. And you find two numbers that multiply out to negative 14 and simultaneously add up to minus 5. Yep, there they are. So to do the complete job here, we write all of this, x plus 2, x minus 7. And remember, the placement of the signs is terribly important. If we make this minus 2 and plus 7, it's going to make a plus 5 in the middle. We don't want the plus 5. We want the truth, the minus 5.
Can I ask a question?
Sure.
Why did you separate the px to the fourth power?
Why did I pull this out, you mean?
Yeah.
Because then I get something much simpler here, so I can, you know, anytime there's a GCF, whether it's got numbers and letters, or like over here, just a number, you want to get that out of the way, because then what remains will be much easier to work with. That's one reason. The other reason is,
Oh, okay, I see it now.
when you're all done, you want to have factors that cannot be broken down any further. It's just like if you're asked to say, well, what's the prime factorization of 14? And you just say, well, 1 times 14, you haven't done the job really. You want to be saying 2 times 7. Or if you're prime factoring 30 and you say, oh, well, that's 2 times 15. That's not good enough. You have to take the 15 and break it down into 3 times 5. It's the same principle here, except you get variable expressions, not just numbers. Does that answer the question?
Yeah, thank you.
You're welcome. What's the difference between x plus 3, x plus 7, and x plus 3p, x plus 7p? There's that extra letter p in there. And if we multiply this out, you know, we're just going to get x squared plus 7x plus 3x plus 21, which will give us 10x in the middle, right? If I multiply this out, we're going to get x squared plus 7xp or px, and then plus 3xp or px, and plus 21p squared. So we'll get this middle term of 10. Let me write px instead of xp. Oh, what's happening here that's new? We're getting an extra variable, and notice where it appears. It appears after the constant in the factored form, and it appears twice in the result as a part of the middle term and as part of the end term. So our strategy for doing these, where you've got the second variable squared at the end and just first power in the middle, is this. Do a let's pretend for a moment. Pretend it's not there. Just factor x squared plus 9x plus 14. Erase the y for a minute. Don't forget about it. Just disregard it for a moment. And factor this. We need those same two numbers again that add up to 9 and multiply out to 14. And notice I'm going to leave a little extra space there. I'm leaving this extra space. Why am I leaving this extra space? Is that a pun? I'm leaving this extra space so I can pop the y in there. See, now if you multiply that out, you will get back where we started. Does the same thing apply here? How would we factor x squared plus 8x plus 15? We would write x plus 3, extra room, x plus 5. Right? Those add up to 8 and multiply out to 15. What's missing? The letter a, the variable a. So I'll put an a in there. And now if we would multiply that out, we would get back the original expression. Whoops. There goes Steve, crazy hands. 2m minus 35. Two numbers that multiply out to negative 35 and add up to positive 2. Anybody thinking of them? Okay, if there isn't a GCF in all three terms, then we just go with the other types of factoring. What are we going to use here? A +7 and a -2. Right, those multiply out. I'm sorry, not -2, -5. Those add up to +2 and they multiply out to negative 35. And of course, we're not factoring that. We're really factoring that. We need to insert the variable W. Now that's done. Okay. We've got about 18 more minutes. Let's see. Well, this is just a rerun of what I did earlier with the 24. So, you know, you can try this later if you put a -60 in there instead of putting the 24, and you'll get the lists for all the ways you can multiply and get -60 and what they add up to. So in general, if you want to use the calculator to do this, and I'm not going to do this now because we're getting a little short on time, but try this later. It's kind of fun. There's a ridiculously large number. I don't think Alex or anybody else in this class is ever going to give you something this hard. The textbook might give you. But think of all the different ways you could multiply and get -432. That could take you 15, 20 minutes doing it with pencil and paper. Right? But with the calculator, it's terribly efficient. Now, here's the other big idea for today. Now there's a number in front of the square term. There's a coefficient other than 1 for the x squared term. So numbers that add up to 17 and multiply out to 21, that idea is not going to work here. If you don't believe me, try it. We're going to start with trial and error, and our thinking goes like this. Whatever we put here and here has to multiply out to 2x squared. So there's not a whole lot to choose from. It's got to be a 2x and an x, right? And then whatever we put here and here has to multiply out to 21. So what are the possibilities? 1 and 21, 21 and 1, or 3 and 7, or 7 and 3. So if I put the 7 there and the 3 there, let's give that a try. Put a question mark. I don't know if that's going to work. Let's try it. I get 2x squared, and then I get 6x, and then I get 7x, and then I get 21. No problem getting the 21, no problem getting the 2x squared. I got 13x in the middle. I really want 17x, don't I? Let me try again. This time I'll write 2x plus 3 and x plus 7. This one does work, doesn't it? We get 2x squared plus 14x plus 3x plus 21. And hot diggity dog, there's the 17x in the middle. And so that's trial and error for this one. And I got to tell you, this is a nice one because there weren't too many different things to try. If we go to this, I might try 4x and x there, and 1 and 3 like that. What would that do? 4x squared plus 12x plus x plus 3. So that's making 13x in the middle. No good. If I try 4x plus 1, I'm sorry, 4x plus 3, x plus 1, that makes 4x squared plus 4x plus 3x plus 1, 7x in the middle. Oh, I'm getting frustrated. It doesn't work. Calm down, Mr. Dane. You had too much coffee. We could also do 2x and 2x to make 4x squared, right? And then if I put a 1 and a 3, I get multiplying these, I get 4x squared, and then plus 6x, and then plus 2x, and then plus 3. Thank goodness, there is the factoring. Now I've got the 8x in the middle that I want. Okay. Catch my breath. Let me hydrate. Now for this, I'm not going to even really finish this one. I'm just going to get you to consider what we could do here. We could do 6x and x up in the front. And then here we could do a 15 and a 1. Well, I guess since it's plus at the end and negative in the middle, they got to both be negative, right? And then we could try -1 and -15. And then we could try -3 and -5, or -5 and -3. And if none of those work, oh, then we might try 3x and 2x to get the 6x squared, and go through the same rigmarole with all those numbers again. And if you feel like crying, I don't blame you, because this is a long, time-consuming process. So as soon as the numbers start to get to have several possibilities, trial and error is not a very efficient strategy. So here's what we do instead. And think about all the ways you could multiply to get the 6n squared, and all the ways you could multiply and get 20. That's why I wrote really, please note. We're going to use something called the AC method. Hooray for the AC method. It saves us a lot of time. So it's called the AC method because that's where you start. You take the A number, which is the coefficient for the square term, and the C number, the constant, and multiply those together. So for this example,
I have a
6
question.
times 20, yes.
So even if you can easily factor an equation, can you use the AC method?
Oh,
Or
of
does
course,
it have to be?
Yeah, but if you can see how to factor it without the AC method, the idea is get the thing factored and do it as efficiently as possible.
Okay, thank you.
The AC method will work even with the ones with a 1 in the front of the square term, but it's kind of a waste of time there because you got that faster method we studied earlier. Once you get this AC number, we're going to do the same thing we were doing a while ago. We're going to make a list of all the ways you can multiply and get, in this case, 120. 6 times 24. Oh, and then 8 times 15, right? And 10 times 12. And then the next would be 12 times 10. So it starts to repeat. So there's all those possibilities. We're looking for the pair here that adds up to 23. Okay, we did not make a list of how do you multiply and get 20. We made a list of how do you multiply and get 6 times 20, 120. And we're looking for the pair that adds up to 23. Now we go over here and we do this strange business. We're going to rewrite the middle term. All those n's are in a nice little pile, 23 n's. Well, we're going to bust up that pile into 8n plus 15n. See, no change at the front, no change at the back, just in the middle. We take the 23n and replace it with 8n and 15n. And we could put the 15n and then the 8n. It wouldn't make a difference in the final answer. The order does not matter. Now, remember 2 days ago, what do we do with this when it's 4 terms? We do that, right? Factor by grouping. If I take out the GCF there, that would be 2n times 3n plus 4. The GCF here would be a 5 times 3n plus 4. And look at the magic. Feel the magic. There it is, 3n plus 4. 3n plus 4, 2n plus 5. If you multiply that out, you will get our original expression. Okay, without too much fuss compared to how long that could take with trial and error, unless you got lucky. And if you do trial and error, you want to do it in an organized method so you don't accidentally skip some possibility that works, right? So we're going to do a few more of these to make sure we get the hang of it. And that's what this last chapter is about, using the AC method to factor something where it's 2x squared, 3x squared, whatever. And also be able to identify prime polynomials in that type of number, that type of expression. So here A is 6, C is 55. And so I am going to use the calculator to help myself here. Numbers are a little bit big. Go back to here. Oh, you know what? First, I need to know, because I don't trust my brain this morning. What's 6 times 55? The AC number, that's 330. So AC is 330. So my first equation will be 330 divided by x. And my second equation will be 330 divided by, divided by x plus x. And now I'll just go to table. And what am I looking for? I'm looking for, in this third column, the sum of 43. The middle term is 43x. So I'm looking 43, come on, 43. There it is right there. You see that? If I do 10 times 33, I get 330, and 10 plus 40, 10 plus 33 is 43. So now I go back to the paper and write, these are my new best friends, 10 and 33. So I'm going to take the 6x squared, and I'm going to replace the 43x with 10x plus 33x, or 33 and then 10, it doesn't matter. And then the 55. And now we will do the factoring by grouping. Common factor there would be 2x times 3x plus 5. And the common factor here would be plus 11, 11 times 3x plus 5. And notice the nice expected thing is happening. We're getting that common binomial factor, right? 3x plus 5, 2x plus 11. That's the factoring. Even though these numbers were kind of large, we got done in about 3 minutes. The answer, Atul, the answer is yes. You're going to see one of those very soon. Good, very good question. Let's do this quickly by the AC method. 4 times 3, AC equals 12. We need numbers that add up to 8. This goes quick. See, 2 and 6 multiply out to 12. 2 plus 6 add up to 8. And so, oops. I'm going to write plus 2x plus 6x plus 3 and factor by grouping. Factor out 2x there, 2x times 2x plus 1. Factor out a 3 here, 3 times 2x plus 1. And ready to write my answer, 2x plus 1, 2x plus 3. I think this is the same one we did guessing and checking a few minutes ago, I think, right? What happens here? A times C, 10 times 15 is 150. And 6 times 25. Okay, I'm not going to make the whole list now because we're running out of time, but 6 and 25 add up to 31. 6 times 25 is 150. So I will rewrite this, replacing the middle term, replacing the 31x with 6x plus 25x. And then GCF there is 2x times 5x plus 3. GCF here is plus 5 times 5x plus 3. And so the answer is 5x plus 3, 2x plus 5. Cool. 3 times 50 is 150. In this instance, we want our numbers to add up to negative 35. So how about negative 10 and negative 15? No, wait a minute, that's not right. Negative 30 and negative 5. Multiply those, you get a positive 150, and add them and you get the negative 35. So I write 3x squared minus 30x minus 5x plus 50. And what's our GCF here? 3x times x minus 10. And here minus 5 times x minus 10. And factoring in x minus 10, 3x minus 5. Are we good? All right. And this one, I'm going to skip this one because we're running out of time. Now, this will answer your question, Atul. If we do 5 times 12, we get 60. Possibilities: 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, 6 times 10, and then the next would be 10 times 6. It starts to just reverse order. This is the complete list, right? So these add up to 61, 32, 23, 19, 17, 16. We don't see 38 anywhere. And once we've done this, once we've made, let me be clear, once we've made an exhaustive list of all the ways to multiply and get AC, and none of them have the sum of the middle coefficient, B, then we can say it's a prime polynomial. It cannot be factored, not with whole numbers anyhow. Okay. So hope that answers that earlier question. Here's one. What's the first thing we should be doing that your teacher is always forgetting to do? What do we want to do first here? Is it popping out at you? Take out the x, yeah, and also we could take out, I think we could factor out a 3. Let's write 3x times 6x squared minus 11x plus 4. And we're not done. We want to factor what's in the parentheses. So I do 6 times 4 is 24. And I need a pair of numbers that add up to negative 11. How about negative 8 and negative 3? Those multiply out to positive 24 and simultaneously add up to negative 11. So working on that by itself, I'm going to write 6x squared minus 8x minus 3x plus 4. And then the common factor here would be 2x times 3x minus 4. And a little bit tricky here, the common factor here, I'm going to factor out a negative 1 times 3x minus 4 to return us to a plus 4. And what have we got when we're all done here? We've got 3x minus 4, 2x minus 1, And once we're there, we no longer need the big square bracket, so I'll just write 3x minus 4, 2x minus 1. And that's done. Even with that big clunky GCF. All right. I think that's the last example. There's a video here that I made, I don't know, 4 or 5 years ago, showing the AC method again. Oh, no, I'm sorry. It's showing how to use the calculator using the TI 83 or 84 to get the table instead of doing all this by hand. Okay. So here's a summary of what we should have learned today. And when I'm all done, please feel free to go now. If you have to go to an actual class, watch the rest of the recording later. I'm going to go back and do the things that I skipped over. If you care to view those later today, or just stick around. We should be able to factor something like this, where it's a 1x squared, or make a statement that it's a prime expression. Also, when there's that extra variable in there, we want to be able to factor that. And what we've been doing the past little while, factor a trinomial like that, where the square term has a coefficient other than plain ordinary 1. And then we get things like this also. We didn't do any of those. But that's okay. You use the same approach. Just pop in the second variable at the last minute. You're welcome, Sarah, and have a great weekend. Yeah, multiple times taking the quiz. I believe that's only this first quiz. This first quiz is kind of a giveaway. Just it's sort of a practice in how to use the whole system. I mean, I'm not too involved in that. That's your recitation instructor. If you want to make sure you get the correct answer. I don't always know about that stuff. So looking ahead, for one of the things that we're going to use factoring for is solving an equation like this. See, that's factored, right? And if A times B equals 0, if A times B equals 0, then what do we know about either A or B? Then either A equals 0 or B equals 0, or both. On a counter, you can't multiply two things together and get the answer 0 unless one of the numbers is 0, right? With this written in factored form, if we look at this first parentheses, when will this be 0? If we use 3, it'll say 3 minus 3. That'll make that 0. 3 is a solution. 3 will make this true. Using 3 for x will make this true. We'll make this true. We'll make that true. Here, if we would use a -7, we'd get -7 minus 3 would be -10, but who cares, because it's going to get multiplied by -7 plus 7 is going to get multiplied by 0 right there. It'll be a solution. So having this in the factored form, see, if we had it in this form, I can't just look at that and say what x values make that 0, but in the factored form, it's very nice. I can say 3 and -7 will work. Not only that, I can see there's no other possible solutions that I'm missing, that I'm not paying attention to, because the only way to get each factor 0, we've figured that out, 3 and -7. And then why would this be a partial credit answer only? Because the 3x minus 12, that has a GCF that hasn't been taken out. You would want to rewrite that so that it is broken down as much as possible. When you get all done factoring, look at your parentheses expressions, make sure there's not a sneaky little GCF like a 3 that you skipped over. You don't have to go back to the beginning. You just factor it out of that one term. Okay, and this is just the recipe for the AC method. Again, I don't need to read that out to you. And there's that same link to that same video from 4 or 5 years ago. Let me just go back and see which exercises did I skip. Oh, this one, AC here would be 99. And 1 and 99 add up to 100. That goes pretty quickly. All right, 11x squared plus 1x plus 99x plus 9. And the common factor here would be x. We write x times 11x plus 1. Common factor here is 9. We write 9 times 11x plus 1. And writing out the answer, it would be 11x plus 1, x plus 9. Okay. What else did I skip over? I think there was at least one other. I try. Oh. Yeah, let me just do this with the calculator. Feel free to leave if this is just tedious for you. No need to stick around, but I just want to show you the kind of the power of this thing. These are big numbers, right? Negative 432. We're when we mentioned we're back to 1x squared here. So this would be aggravating doing it with pencil and paper. But with the calculator, if I type in negative 432 divided by x, and then negative 432 divided by x plus x, did I type all that correctly? Looks good. And then go to the table. And what am I looking for? The middle coefficient is negative 6. So I'm looking in this column for a negative 6. Keep going. Looks hopeful. We're getting closer and closer. Oh, there it is right there. So with a 18, a positive 18 and a negative 24, we get the negative 6. Let me write that down. Positive 18, negative 24, those add up to negative 6, and those multiply out to the large negative 432. So now, if I rewrite this, x squared plus 18x minus 24x minus 432. Common factor here would be x times x plus 18. And the common factor here, I need a calculator. 432. Does 24 go into that? Yes, 18 times. So I can factor out negative 24, negative 24 times x plus 18. Negative 24 times 18 is negative 432. So this monstrosity, which may have taken 20, 30 minutes without any technology, that took me maybe 5 minutes, even though I was talking and explaining. All right. Was there anything else I skipped over that anybody wanted to see? Guess not.
I had a question, sir.
Yeah, sure.
Earlier, right before you got to section 6.3, you were going over equations that had the additional exponent after the constant.
You mean an additional variable?
Yeah, yes, sir.
Yeah, like the ones with the y's thrown in.
Yes, sir. And my
Right here, I'm
question
on this
was,
page. Yeah, go right ahead. Sorry.
my question was, earlier you had stated that normally when we want to try to rebuild the equation into a familiar format by doing like the exponents descending.
Oh, very good.
And I was curious, how do I catch it to
So you don't do this x squared plus 14y squared plus
Yes.
9xy. Yeah, well, if you did that, and tried factoring it, I think you'd run right into the ground and say, oh, I can't factor this. So the answer, and it's not a popular answer, but it's true. You just have to recognize the thing from having seen it enough times.
Okay,
A big part of this class and all the classes after it is seeing things the right way. And not to be disgusting, but it's like if you go to the doctor with some kind of skin ailment and you think it's a rash, and the doctor will know whether it's poison ivy or if it's a brown recluse spider or whatever the heck it is, just because he's seen the thing a million times, he knows what to look for. So when you start seeing, this kind of symmetry here of the two variables squared to the outside and the first power in the middle, then you think, oh, well, let's see, if I just eliminate that second variable and factor that, does it do this nice cooperative thing of just insert the second variable there, and that works. Another thing I might say, you could use the AC method here with the thing as it is. If you multiply, well, no, I'm sorry, no, I take that back. No, that would be too messy. You could, but it would be too messy. But yeah, it's mainly a matter of experience.
thank you very much, sir.
You're welcome. Thanks for asking us. That's a good question. Anybody else have anything to add before I stop the recording? Anything else before I stop the recording? Okay, and I just remembered I forgot to hit record, so I want us to go back to the very beginning, the part that did not get recorded. The first 3 or 4 minutes of class, we just refreshed our memory about some terminology that the numbers multiplying the variables are known as coefficients. The powers are also called exponents. The variable part of these expressions are the pieces that are allowed to change their value, which in this case would be just the x's. And we often refer to these terms with these words: quadratic term for the term that has the second power, linear term for the plain old x, and the number at the end, if there is one that never ever changes, gets the name constant term, sometimes called the 0-degree term also. And then what you missed, or what I missed by not pushing the record button, is we just did some experimenting here. We said, how can you factor and get x squared plus 2x minus 15? Well, it's got to be that the first two items have to multiply out and make x squared. So there's no choice except to put x in x. These last two terms have to multiply out and make negative 15. So there's no choice except to put these different combinations, because those are the only ways you can multiply and get negative 15 with these numbers that you see here. We tried them out, and finally the last one worked, giving us the 2x in the middle. The difficult part is getting that middle term to come out correct. There we got these results, and wasn't until the fourth try that we got it to come out correct. Then we made the observation that when it's just a 1x and a 1x and a 1x in all three places, the two numbers that are used will make the middle coefficient when you add them, and will make the constant term when you multiply them. And so that leads to the factoring strategy for something like this, of just find two numbers that multiply out to the number at the end, and at the same time, the same two numbers add up to the number in the middle. So when we got down to here, and I think by now I pushed the recording, but I'm going to play it safe and say this again. If we make a complete list of all the ways you can multiply and get 30, and add those pairs up, find the pair that adds up to 11, then you've got the factorization. Find the pair that adds up to 13, and you've got your answer. Okay, and if you had, look, here's the 30 at the end again, right? At the end again, right? Is there any way to add the pairs and get a 7? No. So we would say for that reason, this is also prime. Because looking at every possible combination of numbers that multiply out to 30, none of them add up to 7. Doing this is impossible. Factoring this is impossible. Okay. Are we ready to stop the recording? All right, I'm stopping the recording. Recording watchers, have a nice weekend.